Hi guys, today we will be discussing problem number 1420 in Leetcode, which is a build array where you can find the maximum exactly k comparisons. So the problem says we will be given three integers n and m and k. So we need to return the number of possible arrays with given constraints. So they have given some constraints. So constraints are they have given one algorithm, so where it is returning the maximum values index in that algorithm. Also, while calculating the maximum values, it is also updating the search cost. Search cost is basically it initialize it to 0, and every time we are getting a new value, let me annotate. So search cost initialize it to 0 every time we have the maximum value. We are updating the search cost by 1. So it is basically the number of times you are updating the maximum value. That's it. So that search cost should be k, and we need to create an array of size n, and we need to and the range of the numbers inside the array is from 1 to m, and the search cost should be equal to k exactly. So yeah, I mean, well, we don't need to return the exact arrays and its elements. We just need to return the number of possible such arrays. So since the answer is long, so we can take a modulo of 10 power 9 plus 7, and we can return that. So how do we do it? So by looking at the problem, it might look impossible, because I mean the number of possible arrays are very high. And yeah, I mean, let's try to break down the question, and then let's see what can we do. So let's take this example n equal to 2, and let's see how do we do it. So let's say n equal to 2, m equal to 3, and k equal to 1. So we need to have such cost of 1, right? So we need to update the maximum value only once. So once we update, once we have some maximum value, once we update any value, we don't need to, when we cannot update it further, and that's the, and the following element should be less than or equal to that element, because that is when we'll not update the search cost, right? So possible values will be the, I mean, at first we can have anything 1 or 2 or 3. So let's take 1, 2, I mean, that's, it should be a fair size 2, right? I mean, why 3? Because the size of the array is 3 only. So now, so if we put 1 here, what can, I mean, the search cost will be 1. If we put 2 also, search cost will be 1. If we put 3 also, search cost will be 1. So we have achieved the search cost. So the next element should be less than or equal to the max so far. So we can put 1 here. Here we can put 2 or 1. Here we can put 1, 2 or 3. So total how many elements are there? This is 1, 2, 3, 4, 5, 6. So answer will be, for this it will be 6, right? So it is 6. So like this, let's also take one more example. N equal to 5, m equal to 2, and k equal to 1. No, k equal to, k equal to 3, right? So I mean, can we construct an array where we need to update the maximum value 3 times, but the max possible value is only 2? I mean, we need to take numbers from this range only, but we need to update the maximum value 3 times. It is not possible, right? So maximum we can update 2 times only. I mean, if we take this array, it will update only 2 times. I mean, you can increase the size. You can write as many ones as you want or twos you want, but it will not update the search cost. The search cost will still remain same as 2. So we cannot achieve search cost of 3 with n equal to 5 and m equal to 3. So let's I mean given so let's take one example and see how we can fill the position. So let's take one state one, let's take one example 146 and 2. Let's try to see the all possible values that we can fill here. So here there are two possibilities. First one is we can update the I can update search cost. Update by update, increase the search cost, or we can keep it same. We can keep it same, right? Two possibilities. So if we want to update the search cost, then we need to put in the number which is greater than the number that we have so far. So we can, if the numbers range is from, if m equal to 10, so the numbers range is from 1 to 10, right? And let's say here n equal to 5 and m equal to. So don't go into these values. I'm just giving this for this example purpose. Just concentrate on how we can fill this particular position. Yeah, I can modify whatever values you want. So there are two possible ways. One, we can update the search cost and we can keep it the same. To update the search cost, we need to put in the number which is greater than 6. Whatever we have so far. So we can put 7 or till 10, 7, 8, 9, 10, anything we can put so that the cost will get updated. And here, if we want to keep it the same search cost, we don't, if you don't want to update it, then here we can put any value from, so 1 to 6, right? So if you put any value from, if you put 1 here, it will not increase the search cost. If you put 2, it will not increase. 3, it will not increase. 4, it will not increase. Why it will not increase? Because whatever we put, it is not greater than 6, right? The search cost will get increased only if you find the new maximum. So yeah, with this approach, we can actually derive some formula. So let's take something called as dp. So at every time we need to maintain three states. One is the index that we are at, and then the next one is the maximum value that we have seen so far, and number of remaining times that we need to update the, number of times that we need to update search cost. So remaining search cost. So this means if we are at so we are at index, we are trying to fill index ind, and we have seen this maximum number so far, and we need to achieve this many times k, this many times search cost. So how do we do it? So for this every time, right? So there are, yeah, so two formulas as discussed, right? So if we don't want to update the remaining, right? So if we don't want to update the remaining, then the formula will be yeah, then we can put number of, okay, maximum plus 1 to the m range. So in this range we can put all the numbers, and we can call the dp of this many times of dp of this ind plus 1, and this the mu, whatever we put mu max value, mu max, and this m will get reduced by 1, right? And here in this case, if you don't want to update the search cost, then it will be dp of ind plus 1, and then the max value will remain same, and then remaining will also remain same because we haven't updated the number here. So I mean, I'll write it down to be more clear. My drawing might not be clear for you. So yeah, I mean, two possible cases. So one is max value star dp of ind plus 1. I'm just giving you the dp formula, and then we can implement it by using this. So, and then max value will be the new max, and then remaining will get decrease it by 1. This is the first case, and the second case will be the numbers we have so far. uh, no, this is not new max. The max will not change in the first case. This is when we are not updating the search cost, and when we are updating the search cost, then it will be, I mean, then we will be having new max value. So when how many times we have new max, we will call this dp with ind plus 1, and then this new max value will change, and then remaining will get decreased by 1, right? So this is the formula. So here we are trying to fill this array, right? So at first we don't so let's comment it. At first we don't have any number, so it will be, where at index, so current index will be 0, and current max, so we haven't put any number, so max equal to 0, and k will be, I mean, it will be k only, right? So let's write some helper function which will take this I mean, fill the which will take these values and return us the answer. So ind, and we have max so far, and then the remaining, right? So I mean, let's use memoization, and so let's, okay, maybe first I'll tell you the recursive solution, and then let's do memoization later. So yeah, what this helper function will do, it will take the current position, current state where the index is at, and the maximum value so far, and the remaining number of times that we need to increase the count so that we achieve, we increase the search cost count so that we achieve the given constraint. So it will be of ind, of max, of that we have. So we can use this function, but why I have used the new function, new helper function, because I mean, when we are writing memoization, we cannot use this. So yeah, for that purpose only I've created this new function. I'll also include that memoization later here, right? So let's, what if we reach the end? Or, I mean, let's try to create the base case, right? If we are at the end, if this index is equal to this size, right? So let's make this n and m as global variables. So this dot n equal to n. Yeah. Okay. If we have reached the end, then we have two possible ways. If I mean, remaining, if we don't have anything to increase, I mean, if we have achieved what is asked, then we can return. 1 from here. Else, if remainder is not 0, if we still need to increase the count, if we still need to increase the search count, then we have not achieved. This is not the correct answer, so we need to return 0. Also, if remaining is less than 0, right? In this case also we will return 0 because yeah, we need to have exact k comparisons, not less than that. So here, so let's take result as 0 and two possible cases, right? So case 1, when we want to increase search cost, and case 2 is when we want to maintain the same search cost. So two possible ways, right? So when we want to increase the search cost, then we need to update the maximum value so far to the, see, we have this one, right? So we need to iterate from this value. We need to iterate from int equal to max plus 1. So we can put this max plus 1 value and we need to iterate till m. So this is the maximum possible value that we have, right? I mean, that we can put in this array. And then I plus plus. So the new max now will be plus equal to res plus. We will call this helper function with index will get increased by 1 and the new max value will be I, and remaining will decrease it by 1. Right. So this is the first case, and second case when you don't want to um, increase, I mean, when you don't want to increase the search cost, you want to maintain the same, then we will be iterating from 1. I mean, we can put any number from 1 to the max number that we have encountered so far, and then res plus equal to, I'll tell you why I'm writing res equal to res plus instead of res plus equal to, and yeah, helper of, we will be increasing the index, the max value will still remain same, and remaining also will remain same. Then we return the max value. So here why I'm not writing res plus equal to is because we need to take modulo, right? So every time we are updating the res value, let's take percentage of mod will be equal to mod equal to 10 to the power of 9 plus 1. Therefore, it will be, so this is basically 10 to the power of 9 plus 7. So we need to do the same for this one. Percentage of mod, and we need to return this. Yeah, this should work. Let's try to check quickly. Mm, Mining is still okay. Yeah, let me see where this is wrong. Yeah, my bad. I'm returning max from here. Need to return this. So yeah, this is working, but we can improve this solution further. I mean, if we try to submit this, it will definitely give time limit exceeded because yeah, mm, it is doing a lot of repetitive work. So let's try to memorize the work that we have done so far and then use it without repeating the work. So yeah, right. When we have calculated this, when we calculated for let's say for this, we can store it using memorization, and then we can reuse it for the same, and let's say for the same and I index and max value and the remaining. So let's create one array, 3D array, which will call memorization, and let's initialize it inside this. New int of size array, and then we'll need. So why m plus 1 and k plus 1? Because I mean, if we have m, then we will have it till m minus 1 only, right, index. So, but we need maximum value of m plus 1. It's not m minus. So, we need maximum value of m. So we need to take till m plus 1, and same with k. And we need to have exact k comparison. So to get kth index, we need to have size of k plus 1. And same for this. And this represents the size. So I mean, these two are representing the index values. So that's why we'll have to take plus 1 for this. So, and let's initialize the values. So I'm initializing the values as -1 so that we'll know which value was calculated already and which value was not. So before returning, so we will put memorization of ind and max value and remaining equal to res. And when we come here, before even initializing the res only, if we have already calculated memorize this value earlier, if memorization of ind max and rem is not equal to -1, which means we have already calculated this earlier. So we need to return the same rem of ind max and remaining. This should work. Let's try to submit it quickly. And yeah, it got accepted. So that's it. So here we have done top-down dynamic programming. So we can also, I mean, without this recursion, we can also do bottom-up, but the complexity still remains same. So I mean, it's personal preference if you want to do it using functions or you want to do it iteratively. But yeah, recursion takes much space, but that is very negligible. You can neglect it. Even though it is order of one, even though, but still we have array size. I mean, we have 3D array here. So yeah, we can neglect that. And yeah, and that's it for this question. Thanks.